So in this example, we're dealing with a sample of size n with y1 through to yn rather than x1 through to xn. Nothing changes, but here's your distribution as well. And we know that y's are positive, and we know that our alpha parameter is also positive. Okay. And using this, all we have to do is find the MLE of alpha. And just like before, we follow a series of pretty simple steps. So first and foremost, calculate the likelihood, which is the product of all of your individual densities here. So that's from I equals 1 to n of, I might write this here as 2 alpha to the negative 1, just personal preference. And then this is going to be y sub I, because we're doing it for each of our y's. And that's going to be e to the negative y sub I squared over alpha. Okay. We then take the log likelihood, which is simply just the log of the likelihood. And what we do now is apply the natural logarithm. So this product is going to turn into a summation when we apply the log to it. And if we log the first term, we get, inside here, we get the power comes down to the front when we log. So negative ln 2 alpha. This one's just going to be plus, because we're timesing, so plus ln y sub I. And then this one's going to be plus ln e to the negative y sub I over alpha squared. And with logs, we can take this power to the front, and ln e is just 1. So this part here is going to be negative y sub I squared over alpha. Cool. And we can sum this, so what's going to happen here is that we have no subscript here, so we can just, do negative ln 2 alpha plus negative ln 2 alpha n times, so we get negative n ln of 2 alpha. And this guy here has an I subscript, so we do have to leave that summation the way it is. So summing from I equals 1 to n of ln y sub I. And this one over here, I might write as minus the sum from I equals 1 to n of y sub I squared, and I'll take that as alpha to the minus 1. Okay. So we can now differentiate this with respect to alpha, and once we do that, we get del L on del alpha. How do we differentiate this guy over here? That's just going to be negative n over 2 alpha multiplied by the derivative of the inside, which is 2, which actually cancels. This derivative with respect to alpha is 0, and this one, we can bring the power to the front. So if we do that, we get plus the sum from I equals 1 to n of y sub I squared alpha to the negative 2, or over alpha squared. Okay. And setting this equal to 0 for stationary points will eventually show that it's a maximum, but let's just set that equal to 0 for stationary points. And then all we have to do now is just sort of solve for alpha. So what we can do is say negative n over alpha. We can take the 1 over alpha squared out, so plus 1 over alpha squared times the sum of all of your yi's squared, and set that equal to 0. So now I guess what we could do is multiply by alpha squared everywhere. That's going to get rid of the denominators. So this becomes negative n alpha plus the sum from I equals 1 to n of y sub I squared is equal to 0. And we want to solve for alpha, so we can just move some terms to the other side. This becomes n alpha is equal to the sum of all of your y sub I squareds, and then we can get our alpha according to maximum likelihood estimation, just dividing by n, so we get the sum from I equals 1 to n of y sub I squared over n. Okay, and we've got our maximum likelihood estimator. To show that this is a maximum, we'll take the second derivative. So just recall from memory that our first derivative was, well, it's just over here, isn't it? So what we get is del L on del alpha is nothing but, looks like negative n alpha to the minus 1, if we just write that as a negative indice. And then this guy here is plus the sum from I equals 1 to n of y sub I squared over alpha squared, which I'll again write as a negative indices. So y sub I squared alpha to the negative 2. So if we take this second derivative, del squared L on del alpha squared, what we get is n alpha to the minus 2, so n over alpha squared. And then this guy here is going to be minus taking the power to the front. So minus 2, sum from I equals 1 to n, y sub I squared alpha to the negative 3, so over alpha cubed. And so how do we show that this is negative? Well, you'll notice that this sum from I equals 1 to n of y sub I squared is pretty close to our maximum likelihood estimator. So first and foremost, what I'll do is I'll patch it up so that we can make it look like our maximum likelihood estimator. But if we're going to patch it up here, we're also going to have to patch it up. If we're going to divide by n, we're also going to have to times by n at some stage. So what we can now do is substitute in our maximum likelihood estimator. So what we can say is n over alpha hat squared minus 2n over alpha hat cubed. And then this guy here is just alpha hat on its own. So alpha hat. And so now we can cancel the alpha hat and the part of the alpha hat cubed, which becomes a squared now after we cancel. So this becomes n over alpha hat squared minus 2n over alpha hat squared. And you'll see here that negative n over alpha hat squared is definitely negative because squaring is positive and we're taking the negative of our sample of size n. So that's definitely going to be less than 0. And because of that, we get this as our maximum likelihood estimator. It is, in fact, a maximum, and that's really it. So that's your maximum likelihood estimator of alpha.